Thank you so much for the kind introduction. So hi everyone, my name is Roy Schwartz, and today I'll be talking to you about green AI. Okay, so before I begin, just a couple of words about myself. I'm a senior lecturer at the School of Computer Science at the Hebrew University of Jerusalem. My main field of research is artificial intelligence with a focus on natural language processing, or NLP. So most of the examples I'll be giving here are from this domain, but I think many of them apply to other domains, including computational biology. And my main research interests are in understanding AI models, in revealing the biases in those data sets, and in making AI more sustainable, which is the focus of this talk. So when we think about AI today, we've seen tremendous success in a wide range of fields, and we have machines that can translate text from different languages. We can communicate with our phone by just using our voice. And we can have machines that beat world champions in games like Go or poker. And we have tools that can recognize objects and faces in an image. And when you think about the current crisis the humankind is facing at the moment with COVID-19, which obviously touch on the topic of computational biology, we're also seeing AI at the front, helping scientists find both vaccines and curements for this pandemic, and as well as AI helping scientists to make some sense in all of the large amount of data that has been collected around this. So we're really seeing AI. This is a really exciting time to be working in AI. But at the same time, there's another trend that has been a little more silent than this trend of major success, which is that AI models are becoming bigger and more expensive. So here's an illustration of what you see on the y-axis is the amount of computation required to generate a state-of-the-art model, and on the x-axis you see the year. So on the left-hand side we see AlexNet, which basically started the deep learning revolution, and many would say, and at the far end you see AlphaZero, which is the tool that DeepMind used to play Go. And so what you see here is an exponential growth in the amount of computation between these 2 points, which amounts to about 300 times more computation being used in the period of only 6 years. And indeed, this is not something that stopped in 2018. We're seeing this trend continuing over the past few years. And this trend creates several problems that I will be trying to illustrate throughout this talk. First of all, when you think about the amazing growth in the amount of computation required, this creates a large price tag per computational model and create the problems of inclusiveness, or in fact, lack of inclusiveness, because the amount of money required to generate these state-of-the-art results is growing also in a very steep pace. And we're seeing some of the recent projects costing up to millions or even dozens of millions of dollars just to train a single model, which obviously leaves out the great majority of the research community and only leaves in the very big and rich organizations. And to give an illustration, here's a similar graph to the one I showed you a couple of slides back, just in the field of natural language processing. You're seeing on the y-axis the number of parameters and in the state-of-the-art model, and on the x-axis you see the time again. And what we see also here are points along this curve with the organization that published them. So as you can see, almost all of these points come from large companies such as Google, Microsoft, NVIDIA, and Facebook. And so if you think about it, the academics like myself and like many of the attendees here, I believe, do not have the correct budgets to participate in this game. A second problem that arises with rising computation is relates to the adoption of the technology. Basically, because we're generating models that are so big, requiring billions or even trillions of parameters just for a single model, we're starting to wonder whether we're just building it for ourselves or whether this is a technology that someone outside can use. Basically, you can't fit on this phone a trillion parameters. And so to build a model like this, it becomes a question of what is the benefits of doing that. And finally, and perhaps most related to this session, is the environmental aspect. So what we're seeing here is a result from a paper published in 2019 by a group from the University of Massachusetts that tried to quantify how much carbon is being emitted by training state-of-the-art natural language processing models. And they made comparison to several other standard events that contribute other amounts of carbon. So as one example here, you can look at training as an NLP model, state-of-the-art NLP model in 2019 with neural architecture search, and compare it to the amount of CO2 that a car emits in the course of its lifetime, and you see that the AI model consumes as much as 5 times the amount that the one car would emit in its lifetime. So this is starting to become a troubling effect. And to say a little bit more about the relationship between AI and the environment, so we're starting to see evidence around the most expensive experiments, the ones that are most expensive in terms of money, in terms of energy, in terms of carbon, and so on and so forth. And as I showed in the previous slide, they're starting to become something that's non-negligible, something that is real, it has a significant carbon effect. But at the same time, these experiments are only run a handful of times because they're so expensive, and because so little organizations can afford to run these models, to train these models. Only a dozen or so such experiments are being run in a given month or a given year. But at the same time, we're starting to wonder, what about normal experiments? Experiments that are that do not require millions of dollars, but maybe hundreds or thousands of dollars. But as a result, they're being run hundreds or thousands of times a day by different researchers around the world. So when you think about the carbon contribution of contribution, quote unquote, of course, of AI, you have to think about these experiments as well. And perhaps most significantly, you also have to think about inference. Inference, basically, once you have a model trained, now you want to run it on a new example. And these experiments are particularly much cheaper than the training experiments, though they're also increasingly more expensive. But these are run perhaps billions of times a day. Think of a Google Translate query, or a recommendation on Amazon, or some movie editing on TikTok, and so on and so forth. And in fact, there are some estimations that say that 80 to 90% of the AI computation is being spent on inference. So perhaps the biggest question that we have in front of us to estimate the amount of carbon being released by AI is, how do we measure that, and what's the right tool to use? And we'll talk a little bit about that, but there's lots of very interesting research going on this topic. So with these things in mind, myself and colleagues of mine, former colleagues of mine at the Allen Institute for AI, published an opinion piece titled Green AI. In this paper, we discussed these 3 problems that I just presented: the problem of the inclusiveness, of adoption, and of the environment. We titled this operation Red AI, of just getting better results by putting more and more computation into these models. And then we presented an alternative, which we titled Green AI, which presents 2 main ways forward to help mitigate these concerns. One is to do enhanced reporting of computational budgets. Basically, think of it as adding a price tag to scientific results. And the other is to promote efficiency as a core evaluation metric for AI, in addition to accuracy. Basically, not only measure how well our model does in, say, recognizing images in faces, or translating from English to French, but how much energy it consumes, how much time it takes to run it, how much parameters the model contains, and so on and so forth. So in this talk, I'm going to be talking about these 2 aspects of Green AI, the reporting or efficiency. And and before I begin, I want to say a point that it's important to not get the wrong impression. I'm trying to argue here that we should ban big models. I think big models and big and expensive models are very important, and they help us push the limits of the state of the art. And in many cases, actually retraining a big model on a lot requires a lot, on the one hand, a large amount of computation, but at the same time, models that get released by their developers help to save others the compute of training them, so they can actually be thought of as a green operation. And in fact, large models are sometimes potentially faster to train than smaller models. So there's lots of complexity here with respect to big models and small models. But the argument that I'm trying to make here is that training big models have concerning side effects regarding inclusiveness, adoption, and the environment. And our goal is to mitigate these side effects. Hopefully, keep the big models, keep this line of research, which is very, very valuable, but try to find ways to mitigate its negative side effects. Okay, so in the outline of this talk, I'm going to start by talking about how do we do enhanced reporting, what exactly is the problem here, and what are some tools to address it. And I'm going to talk about efficient methods for AI. I'm going to present a few examples and talk about interesting open questions. Okay, so let's start with the first part of enhanced reporting. And to give an illustration of the problem here, consider this example. Say you have some task where you're trying to compare between two models, call them model A and model B. And you have some, say, F1 measure that tells you which one is better. And typically in F1, we think that higher is better. So, and you run two experiments and you get these results, and your conclusion is that model A is better than model B because it gets a higher F1 score. So a group of researchers from the University of Darmstadt in Germany tried to challenge this assumption, and they took this experiment using the same two models on the same data set and repeated them multiple times with different random seeds. And what you see on the right-hand side is the two histograms of the blue model and the green model. And you find actually that if you run multiple times, run these models multiple times, not only does the blue model not outperform the green model, but in fact the green model is both slightly higher and has a lower variance. So in many cases, you would actually think that the green model is better. So what is the right comparison to do here between different models? Do we take one example, 10 examples, 50 examples? These are interesting and open questions. Here's another example from a group of researchers at DeepMind. What they did here is trying to compare between different language models. Language modeling is a task in natural language processing where you're trying to predict a word given a previous sequence. And so, for instance, if you have IHN, you're likely to get things like apple or cherry, and not cherry, apricot perhaps, and not a dog or a couch, for instance. And the way the performance of these models is measured is using evaluation matrix called perplexity, in which lower results are better. And they took an LSTM, which used to be the state of the art in NLP, and they compared the performance of an LSTM model compared to the state of the art models on these tasks, and they showed that an LSTM, a vanilla LSTM at least, does not perform as well as our best model. That the LSTMs gets about 80 perplexity points, and the best models we have get between 60 or even slightly lower than that. Again, lower is better in this task. And what they did was they reran the LSTM baseline, but by carefully tuning their hyperparameters. They ran 1,500 trials of the same experiments with different hyperparameters, say things like the random speed, learning rates, and dropout value, and so on and so forth. And they found actually that if you tune the LSTM well enough, you get results that are within state of the art, in the round of 60 or even slightly lower than 60. So we asked ourselves, what is the correct conclusion here? Does an LSTM perform much worse than state of the art or similar to the state of the art? What would have happened if you would take the state of the art model and train them for 1,500 times with different hyperparameters? Again, thinking about what is the correct comparison to be making between different models. And so to conclude, maybe the current way that we're making comparison between models by asking whether model A is better than model B, by using the proxy whether the performance of model A is better than the performance of model B, should be replaced with something like this, maybe asking whether model A is better than model B, given some budget, some constraint that we have. So, let me give you now one particular way to implement this idea. This is the work that I did with colleagues at the Allen Institute for AI and the University of Washington. And the idea here is simple. Say you've run a set of experiments, and you have a set of experimental results, V1 through Vn. And now, typically what you would do is take the max of these validation results, call it V star, and report that. This will be the best result that you can get with this model, and this is what you would report. This is what we've seen in a previous slide, for instance. In that slide, obviously, we would take the mean because we're trying because we're thinking that lower is better in this setup. And now we're proposing a different criteria than taking just the max, but which we call an expected validation performance. In expected validation performance, we're trying to take the expected value of V star k given a certain k. Now, what does it mean? It means that if we run n experiments, we're not necessarily interested in the best result overall, but we also care what would have happened if we would have a smaller budget, some budget of k smaller than n. So let's look at a few examples. What happens if k equals 1? This is similar to taking the mean value of the n values that we have. So if we have, so if we run n experiments and wanted to get an estimate of what we would get if we would run just one experiment, probably the best thing we could do is average these results. If we go to k equals 2, this is similar to taking all pairs of results, taking the max out of each of these pairs, and returning the average value of these. And so on, if we reach k equals n, then the V star n would just be the max, just to be the standard thing that we're reporting. Now, to illustrate this, let's look at a simple example. What we're seeing here is some toy experiment that we run. When we see on the left hand, on the y-axis, the expected validation accuracy, the measure that I just introduced. On the x-axis, you see the hyperparameter assignments, the number of them. And we have two lines that compare two different models. Now, what we're seeing here is an interesting observation. If you would have a low computational budget, say you want to take this graph and try to get advice on which model you should be using, but you only have 10, your budget only allows us to run 10 hyperparameter experiments, then the LR, the logistic regression variance, would be the choice that is better for you, because on lower budgets, this model is more stable and gets, on average, better results. On the other hand, if you have a high budget, if you have more than 12 or 15 hyperparameter assignments that you can run with your budget, then you would better use the CNN. So this gives an illustration of the trade-off between the two, and saying that one number is just not enough to give you a correct answer. Because again, if you think about what would be the standard practice in this case, if you ran 50 experiments, you just take the rightmost points of each of the graphs and reach a conclusion that CNN is always better than logistic regression. But this is, as we see here, not the case on lower budgets. So so now that we have kind of an understanding of what is the problem and what is the partial solution, let's talk a little bit about open questions that we have around reporting. And a very interesting and important question is how much would we get by pouring more computational research into our problem? So what we've seen in the previous slide is that we can take the results that we already ran. We ran 50 experiments and estimate how much would we get if we run 10 or 20 experiments. But what happens if we have 51 or 60 or 100 or 200 experiments? Can we try to extrapolate from the 50 to basically try to estimate how much would be gained by you running more experiments in each of the methods? And another very interesting and important question is, what should we be reporting? We've talked about various things we can measure in terms of efficiency, talking about the number of experiments overall, talking about the amount of time it takes us to run our experiments, the amount of floating point operation, the amount of carbon that's being released, and so on. And the question of what exactly to report and how to measure each of these quantities and how to find a value that aggregates all of these quantities together is a very important open question. Okay, so we've talked about enhanced reporting. So let's now talk about the second goal of green AI or green NLP, which is working with efficient methods. So when we think about how AI looks today, most of the research papers in AI are trying to come up with a new scientific results, and typically these scientific results manifest itself as getting higher accuracy on some tasks. So here's an example from our Green AI paper where we took three conferences in AI, the ACL, the leading conference in NLP, CVPR, which is the leading conference in computer vision, and NeurIPS, which is the leading machine learning conference. And we took a sample of 20 papers for each conference, and we tried we read them and we tried to evaluate whether their main contribution of each of these papers is a higher accuracy on some tasks, is a more efficient method on some tasks, both or other. And we see in all three cases, the dominant approach is trying to improve accuracy. And again, we're not trying to argue that people should not be working on improving accuracy, but our point is that we think this graph could be more balanced. More effort should be made towards making models more efficient. So when we talk about efficiency, there's an important question that goes back to the issue that I raised a couple of minutes ago about what are we trying to make more efficient? Are we trying to make training the model more efficient? We're trying to making inference running more efficient, or making perhaps model selection, the process of taking multiple runs and choosing the best one, more efficient. And similarly, we can ask, what are we trying to measure? What is the quantity that we're trying to make more efficient? Whether it's making the model smaller in terms of space, in terms of number of parameters, taking less time, or using less energy. So let's look at a couple of examples of methods that make models more efficient at inference time. So what we're seeing here is BERT, which is one of the most popular models in NLP. And I chose it to illustrate the first approach to efficiency that works by taking a large model, like on the left-hand side, and making it smaller. So we have a few examples of methods to do that. And the first method is called model distillation, in which we have a large teacher model, and we're trying to learn a smaller student model to mimic it. Again, taking a larger model and trying to learn a model that will do the same job just with fewer parameters at inference time. We can think of pruning as another approach where we take a model that's dense in its parameters and try to prune away some of the parameters. And we can think of quantization, which takes a model with high precision floating point numbers and learn a similar model with lower precision. So all these methods have in common that they require you to train your big and expensive model to begin with, but try to find a way such that it will have a smaller model at inference time that would save on compute at that time. Another example, another line of research talks about making models more space efficient. That is, making models not run any faster and not save any energy, but just take up less space. So they, for instance, get fit on our phone or on other edge devices. So two examples here are weight factorization, where we have, instead of saving a large matrix of n by n, we're decomposing the matrix into two smaller matrices and multiply them. This allows us to save many of the parameters, but basically it does not make the model any faster, for instance. Another idea is to do weight sharing, where we take some of the matrices in our model and force them to be the same. So, for instance, if our model has two matrices, we can force them to be the same. So we're saving half of the parameters. But again, we're not saving any of the training time or inference time. And finally, we can talk about methods to do early stopping. So this allows us to do efficient model selection. Again, think of hyperparameter search or random seed search. And the main idea in most of these approaches is to run multiple experiments, but stop the least promising ones early on. So basically, if we have a budget for 50 experiments, we start by running all of them, but maybe stop and make a stopping point after one epoch, and then see which ones are most promising, and terminate all the others. Again, these are a few of the methods that have been proposed, or a few of the lines of research that have been proposed to promote efficiency. But there are still lots of open questions regarding efficiency that are very important in order to address the challenges that we've talked about. The first one is how do we train sample efficient models that require less data? And as a result, using less data would allow us to label less data. It will allow us to generalize better to domains that don't have much data. And it will allow us to run our models faster because each data point requires some amount of processing time. Another interesting question is what makes a good sparse structure? We've talked, if you recall, a couple of slides back about tuning models, starting with a dense model and turning into a sparser model. So can we train sparse models to begin with? Can we identify what are the key properties of these models and train them to begin with so we don't have to go through the large model that is dense? And similarly, and regarding the last point, can we know in advance what makes a good hyperparameter or random seed? Can we identify these the training runs that are likely to be successful early on? When in that case, and with this, we don't have to run any of the least promising experiments to begin with. Okay, so I want to end by presenting some of the initial results of our efforts towards Green AI. First, I'm going to say briefly about a few of the things that I've been involved in, and then talk about some larger efforts by the community and beyond it. So some of the things that I've developed over the past few years with my colleagues is first a method to better compare between different models. This is something I talked briefly about in the part about better reporting. I've worked a lot about better usage of our data, trying to make models use less data, both at training time and make them use their data more efficiently at inference time. And I've tried to develop methods that just perform the same operations in a more mathematically efficient way. We have a very interesting result that was just presented at iCourier last month about a model that replaces the transform model and approximates it with very little loss in performance, but runs much faster, especially on long sequences. So these are some of the initial results that my group have shown. But if you think more broadly, our goals are to drive the AI community into thinking more about these problems. And indeed, we're starting to see in the last year or so efficient tracks in the major AI conferences, in NLP and in computer vision. We're starting to see workshops that promote sustainable or efficient AI in various fields. And we're starting to see efforts towards more reproducible science that ties very closely to the ideas we talked about better reporting. And another interesting finding that we started to see in the last month or so, in this last year or so, is that the community is starting to adopt these ideas as well. And in particular, there are large players in our community. And the title here is a paper published by senior researchers at Google a couple of months back that tries to estimate the carbon footprint of training large neural networks. And we're also starting to see things like energy usage clauses or environmental statement clauses of large papers with very high budgets. And we believe this is a very important path forward to be more open and more clear and more transparent about the prices of these experiments and promote ways to make them more efficient. And finally, we're also seeing the general public being interested in some of these ideas. Pieces at the New York Times, GeekWire, MIT Tech Review, and so on, that are basically tools to help us spread the word and get more people on board on our mission. So I want to conclude by, again, reminding you that the two key principles that I was presenting here. On the one hand, to promote enhanced reporting, thinking about doing a better job at outlining the amount of resources, the computational requirements for training our models, and on the other hand, making models more efficient, working on efficient inference training and model selection, and thinking about what do we want to make more efficient, running time, number of parameters, inference time, and so on. And with that, I will finish. Thank you so much for your attention, and I'm happy to take questions.
So that's great. Sorry, that's great. Thanks, Roy. That was a fabulous talk. You've set me thinking about lots of things here. We don't actually have any questions in the Q&A. If anybody wants to ask a question who's an attendee, can you please write there? I mean, I have a question or a comment really, which is, I mean, I think this is a fascinating balance between the effort involved in training and then the application of the network once you've built it, once you have the model. And I don't have that's obviously going to be a very different equation depending upon the application area. And I wonder if you had a feel for, general application areas where one, you can accept perhaps spending a lot of time doing a training, but then you have to really optimize the application of that model because you're going to deploy it billions of times somewhere. So or in other situations where it maybe doesn't get used quite so much. So what's your feeling about that?
Yeah, that's a great, I mean, it's a great question. And I don't think, as you kind of hinted, that there's a right answer here. I mean, as you said, I mean, if you're running your model a billions of times, you can probably spend quite a lot and still have, a minor improvement and make it worth it. So definitely if you're a huge company that has large inference requirements, then you should be thinking about inference. I think that the important thing to notice, I think for me, and when thinking about our AI community, is the importance of making training more efficient when you think about research. Because again, when the only models that are being used are ones that are huge and kind of disproportionately expensive to generate or train, this really leaves out a large part of the community outside. And kind of, I mean, thinking about just who can contribute ideas, who gets to set the agenda of what's the right, I don't know if right is the right term, and what's being studied, what gets more, more credit by the community. And kind of when you need an industry size budget just to run this experiment, you leave all the answer to these questions at the hands of very few people. So I think this is very something that's I mean, somewhat gets unnoticed in many cases, and I think it's very important to pay attention to.
Thanks. I think we should have a discussion about AlphaFold when we get to when we get to the group discussion at the end, because I know Alex Bateman will have some thoughts on that as well, which is the application of this to an area that's very important to us. Loic, do you want to unmute yourself and ask your question?
Yes, sorry, I don't seem to be able to write in the Q&A as a panelist. Yeah, I was wondering, you mentioned the inequalities and the lack of accessibility with huge models that require huge resources. And I was wondering if we start benchmarking on efficiency, part of it, as you pointed out, is influenced by how efficient the data center is. And for that as well, like the big players like Google or Amazon, they have a head start because they pour so much resources into making the data centers so efficient. So do you think there could be a side effect where, again, there would be the same disparities where, the big players would be able to achieve more efficient models just because they have more efficient infrastructures compared to smaller teams?
That's a great question. I mean, first of all, I would like to say that it's great that the big players are putting lots of efforts to making their data center more efficient. I know that, I'm not sure what is their motivation. I'm pretty sure it's also related to saving money, but I mean, saving money is a good cause as it is. And if you save on carbon at the same time, and then all the better. I mean, I try to point out that, I mean, there's lots of ways to measure efficiency. Again, if you go to the end line and think about how do you minimize carbon emission, then I agree that, I mean, the large companies can run it on very efficient centers, have the edge here. But I mean, if you go a step back and think about, I don't know, how do you save on running time? How do you save on number of floating point operations? How do you save on number of parameters? Then, I mean, this is at least this is not necessarily an advantage for the big companies and the way you think about it. Does it make sense?
I saw. Thanks. Sorry, can I think we've got time for a quick comment as well from Adrian Friday from the University of Lancaster. So Adrian's commented as well, and his question of coherence with where the cost is. Another idea would be to bill based on your budget reporting, although in some sense, if compute equals energy, that is somewhat the case. So I don't know, that's a comment, I guess.
Yeah, so probably my other comment's more just echoing Roy's comment, because I do some work in distributed deep learning, and you just see the scale of the evaluation, the scale of the data sets that you have to get to compete with the gold standard evaluations now. You sort of get laughed out during the review process if you're not doing enough compute, essentially. And I think, echoing exactly Roy's sentiment about efficient computing there, we're just not accounting for that sort of growing demand. It's just sort of emerging, and it becomes a paywall at the end of the day. If you can't afford, these huge industrial data centers, you can't compete in terms of your research, so you have to partner with them.
I guess we're going to hear more from you in a few minutes, so that'd be great.
Yeah, but
I'm sure we'll come back to some of these.
Yeah, great.